So if it's helpful, you'll find that most of the time, if you were asked to find the area between two curves, and you can identify a leftmost point and a rightmost point. So if it's a shader region, the leftmost X that got colored and the rightmost X that got colored. And you can, if you sketch in a few of our rectangles, like really skinny rectangles, and it's always the same curve, the same function that gives the top y value, and it's always the same curve that gives the bottom y value, then you can write this integral, guaranteed to work. You're going to integrate from left to right of top minus bottom dx. And just remember what that is. The left and the right, they're find the area under the curve, area between the curve and the x-axis, between x equals something and x equals something. So they're like the boundaries left and right. They're x values. And the top minus bottom, that's an expression for the height of each rectangle, and dx is an expression for the width of every rectangle. So we're finding the areas of infinitely many, infinitely thin rectangles whose height all has sort of like the same function, so top minus bottom. And we're adding up all those areas to give a final answer that's an area. Okay, so that being said, that's great, that worked, that's exactly what we did for those first two examples. You have to be really careful to notice that maybe you thought that was too easy. So on the AP test, they like to make sure they also test you on things that aren't as easy. So you might find that there are cases where you see a picture like this. This one comes from your textbook, but it's modeled after a problem that was on a released AP test. So there's a lot of stuff written in there already. So, but think about that process. Could I write this expression, the integral from left to right of top minus bottom? So it does seem like I don't have any trouble telling what the leftmost limit is. The furthest left x that gets colored in is at x equals 0, and the rightmost x that gets colored in is at x equals 4. But watch what happens when you try to draw your rectangles. When I try to draw this rectangle, the top of the rectangle is bounded by y equals square root of x, and the bottom of the rectangle is bounded by the x-axis, which the x-axis has the equation y equals 0. Okay, so I could do the integral from 0 to whatever of square root of x minus 0. But then look what happens if you try to draw a rectangle over in this part of the picture. The top of my rectangle is bounded by y equals square root of x again, so that part stayed the same. But what's the bottom boundary of my rectangle? The bottom of the rectangle is cut off in this section by the line y equals x minus 2. So since I do not have one single top minus bottom expression that works for the whole area, I have to split this up into separate sections. So you have some options. If you can notice where the rule changed, then we can split up the integral. Remember, we can add together areas. You learned this back in geometry, right? You can add together smaller areas to combine to make a bigger area without any loss or any problem. So I'm going to write two separate integrals because for me, I can tell that at the place where x equals 2, and it's nice because they've given us this picture to sort of help clarify the point, that's where I change from having the top curve bounded by, the top of the rectangle bounded by radical x and the bottom bound by the x-axis. And over in section B, the top is still radical x, but now the bottom is that slanty line y equals x minus 2. So I'm going to split this up into two separate integrals. I'm going to integrate from, all right, so here's my integral. I'm going to separate it into two separate integrals to integrate to find the areas of the two separate sections, which you see in the picture already marked A and B, just to kind of help us. You're not required to mark that on the test or anything. It's just to help us understand, especially this first time. So the first, that section A, my upper limit was radical x, the upper bound of my rectangle was square root of x, and the lower bound was the x-axis, which is the place where y equals 0. And that covered x values from 0 to 2. So this is the integral I wrote for that section, the integral from 0 to 2. That's the bell. Sorry if that just freaked you out. of top minus bottom, so square root of x minus 0. Obviously, you could leave off the minus 0. That's not going to affect the value of the integral. And then to get the area for section B, I'm going to integrate from 2 to 4. Those are x values. Top minus bottom, so square root of x minus, unless I have to use parentheses here because that second function, my bottom function, x minus 2, I'm going to need that subtraction distributed over it. So that's great. You probably got 2 points if you wrote that integral. To evaluate, I'm going to need an antiderivative. In fact, I'm going to need 2 separate antiderivatives because I have 2 separate integrals. So the antiderivative of x, the square root of x, is 2/3 x, because I'm going to distribute the subtraction. 2/3 x to the 3/2 minus x squared over 2 plus 2x. So this next 3 lines is simply me substituting in. I need f of b minus f of a, so evaluate at the top limit minus what I get when I evaluate at the bottom limit. Please, 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 please notice that here, that second integral, when I find this, the antiderivative, and I'm going to evaluate it at the lower limit, I need to subtract f of a, essentially. It's all got to go inside some kind of grouping symbol and make sure that subtraction gets subtracted. Remember,